Welcome to the project demonstration of sizing and analysis of renewable energy and battery system in residential microgrids. So here renewable sources, we are using solar panel and a 12 volt 5 watt solar panel. The output from this 12 volt solar panel is input to the charging of this battery section by using this charging circuits, and also parallelly the system will continuously measure the voltage of the battery and solar panel and continuously displayed on the 16:2 LCD screen. And coming to the microgrid application, by including this inverter circuits and a load, we representing this as a microgrid application. Coming to the sizing and analysis purpose, we are making use of this microcontroller, and sizing means we have added this low sizing of this voltage sensors to monitor the voltage of these input sources. Coming to the input source like solar panel as well as battery, that will be measured continuously on the LCD screen by using this PIC16F72 microcontroller. Coming to the flow, we can charge this battery, and battery ratings are solar panel ratings as we discussed 12 volt 5 watts. Coming to the battery ratings, 12 volt 2 amp. So this battery pack consists of 6 4 volt batteries. In that, three are in series. So we will get 12 volt 1 amp and 12 volt 1 amp. So totally 12 volts 2 amp DC output, and that is parallelly input to the microcontroller through this voltage sensor. Coming to this voltage sensors, two voltage sensors look like same. These are all consist of 10 kilo ohm and 1 kilo ohm. So the purpose is controller can't measure the voltage above 5 volts. So we need to make the input voltage below that. That's why we are making use of this potential divider 10:1. So when I am getting 12 volts input from this solar panel to this voltage sensor, the output of the voltage sensor is 1.2, as the potential divider ratio is 10:1, and inside the microcontroller we multiply that with 10 and we display the voltage on the LCD screen. So we can provide the input up to 50 volts to this potential divider circuit, as the 50 volts coming under 5 volt only. Same for the both voltage sensors. And coming to this charging circuits, so we are providing 12 volts DC input from the solar panel to this one, and parallelly same to this voltage sensor. So on this charging circuit, we can see the diodes which are connected in manner of bridge rectifier. Though we are providing DC source, so the bridge rectifier purpose is to rectify the inputs, means polarity corrector. When you provide the DC inputs, this rectifier circuit will act as a polarity corrector. When we are providing the AC input from the transformer to the same charging circuits, there we will converting the AC to pulsating DC, and that is input to the battery through this capacitor. The capacitor purpose is when you converting AC to DC, rectifier will convert AC to pulsating DC only. The pulses will be removed with the help of this capacitor. We will get the smooth DC. That is input to our battery for charging purpose. Same here also, the rectifier for polarity corrector. If you connect in reverse direction also, the rectifier rectifies that plus to plus, minus to minus, and output to the battery through these connectors. And the battery will get fully charged in a duration of 6 hours minimum, 8 hours maximum, either solar panel or a transformer. So from the both, it will take the same time for 6 to 8 hours charging time. So when we place the more lighting on the solar panel, then we can see the same light indication from this also. As of the no low lighting is there, that's why we are getting the low intensity. Right, we can see the low intensity now. And after this battery is fully charged, we can utilize that for the microgrid application by using this switch to the inverter application. Okay, so here the DC is converted into the AC by using this microgrid. On this one we can see RLC circuit, which will convert the 12 volts DC to 12 volts AC initially with the help of this MOSFETs. So RLC is oscillator which will convert the 12 volts DC to 12 volts AC, and MOSFETs will provide the 12 volts AC to 12 volts 2 amps AC. These MOSFETs, and the 12 volts 2 amps AC will be step up to the 230 volts AC with the help of this step up transformer, and it was given to the loads directly. And coming to this motherboard, there we can see the 7805 regulator, as the controller will work 5 volts only. That's why we are going to regulate the 12 volts DC to 5 volts DC with the help of this regulator. And when we on this, then the system will display the welcome message, and it will display the solar voltage as well as the battery voltage. So now we place the lighting on the solar panel. There we can see the voltage increasing on this. Right, so suddenly we place the more lighting. So So the voltage increases. So like this, when we place this under the full sunlight, we will get around a 14.5 volts, which is sufficient to charge our battery section directly. Yeah, coming to the ratings, finally 12 volt 5 watts solar panel, 12 volt 2 amps battery, 12 volts 1 amp step down transformer, 230 volts to 12 volts 1 amp step down transformer, and inverter wattage is 50 watts maximum load can be handled by this inverter circuits, which will convert the 12 volts DC to 12 volts AC output directly. And on this motherboard we can see reset switch to reset the microcontroller only. It won't erase the program, it will just restart the microcontroller. And this steel plated one is the crystal oscillator, which will provide the 20 megahertz of oscillation frequencies to the microcontroller. The purpose of the oscillation frequencies, in order to execute the instructions inside the microcontroller, we need provide the clock pulse. Per pulse, controller can execute one instruction. Like that, we are providing 20 mega pulses per second, so controller can execute 20 mega instructions per second. Right. So finally, we can off this, and one more time, inverter purpose. Right, actually the whole system will run only on the battery only, like we can see now, inverter as well as microcontroller. Right.